more. Let's wait 2 minutes more and then we can start presentation. Okay, can start. mm, According to the sheet, Carolee and Diana will present first, but uh, he has a they have a class and it'll be limited 12 stories. So we are going to start Tandin and Rodelio first. Tandin, are you ready? Tandin, Rodelio, are you ready to presentation? Are you ready to present your instrument, Tandin?
Yes, we're ready to present.
Okay, let's start.
So, let me see. Yeah. Okay.
It is. Yeah.
Give me 1 sec.
Okay. Take your time.
Yeah. Make it big. Can you see the presentation?
Where we can see your slide.
Oh, that's okay. I know it. Yeah, this. Oh, yeah.
Can you change display setting? You can share your screen and then you can change display setting. Yes. Yes, correct, Dixon.
I think. I got it.
Got it?
Not yet?
No,
It's okay.
I think it's good. Oh,
Oh, was it good?
yeah, it's good.
Oh, so let me do it again.
Yeah,
Okay.
that's
Yeah.
good.
Yeah, sorry about that.
No, it's just fine.
Okay. So today, we're gonna talk about three different instruments that we can use to measure mechanical properties of materials. So the first of them is the universal testing machine. Then we're gonna talk about the sensometer, and we will finish this presentation talking about the strain gauges. So I'm Rogelio. Tenzin. So Tenzin is gonna start with this presentation.
Hi, everyone. Today I'll be talking about universal testing machine and how it works. Simply put, a universal testing machine is a piece of equipment that can apply a controlled force to a material sample, and it can measure the resulting deformation or a change in shape or size. So by doing that, we can determine how strong a material is and how much it can stretch or bend before breaking. So they're typically made up of several key components like a load cell that measures the force being applied, a crosshead that moves up and down to apply the force to the sample, and a set of grips that holds the sample in place. So now this is how a data can be acquired using a universal testing machine. So first, a load cell that can convert the mechanical force applied to the specimen into an electrical signal. And second, a displacement sensor that measures the deformation or displacement of the specimen during the test. For converting the analog signals from the load cell and displacement sensor into digital signals that can be processed by a computer. So the software can display the load displacement curve in real time and calculate the material properties such as stress, strain, modulus of elasticity, and ultimate tensile strength. This is how the software looks. And as mentioned before, this software collects the data and analyzes the results. So this is a machine which is quite different from the one that we've shown before. The machine that we showed before was can only measure up to 2,000 pounds, and this can actually measure up to 67,000 pounds. I would say that the first machine can actually be more we can calculate the results more precisely. So the universal testing machine can be used to test various types of materials, including metals, plastics, you got rubber, ceramics, and composites. The machine can be used to perform several tests, but in this presentation, we will focus on tension and compression test. So as you can see, this compression test is a type of a rigid material, and you can't really see that much of a deformation because it is a rigid material. And as you can see the results here, the deformation is almost 8% from looking at the curve. As we move on, we got a compression test for a hyperelastic material. And this, you can clearly see the deformation as it's being squished or compressed. When you see the compression test results, the deformation is almost 80%. Now, I will hand it to Rogelio to speak about extensometers.
So with the universal testing machine, we can perform compression tests and tensile tests. So a tensile test is just a type of mechanical test that measures the tensile strength and other mechanical properties of the materials. During the test, the specimen is held between two grips, as you can see in the pictures, and the machine applies a force to the specimen in a vertical direction. This force is applied gradually, and the resulting deformation of the specimen is measured by a displacement sensor. In this case, for example, in the pictures, you can see two different extensometers. So I'm going to talk about the two different extensometers that we can use to on tensile tests. So the first one is an axial extensometer. The model is 3542, which is basically an extensometer that can be used to record the data of rigid materials. Say in the pictures that you can see here, the blue specimen is a plastic, a rigid plastic, so we need to use this type of extensometers. But if we have another material, let's say a more flexible material, like a hyperelastic material, we need to use another type of extensometer. This is a high elongation extensometer that helps to record large strain deformations. So these are the results that can be obtained from a tensile test. I'm not gonna give a lot of details about the mechanical properties that we can obtain from here. I'm gonna explain that later, but this is just to show you the curves that you can obtain from this type of test. So here, the use of an extensometer in a tensile test allows for more accurate measurement of the material mechanical properties. Let's say the Young modulus and the yield strength. The figure that you're seeing is an example of a test that was performed for two different for the same material, in this case steel, but using two different type of measurements. The green curve was obtained with the cross head of the testing machine, and the blue curve was obtained by using an extensometer. So as you can notice, the curves are different, and if we measure the material properties, we can obtain very different results. So as you can see, as we know, the Young modulus for steel is around 210 gigapascals, and like the result we obtain with the blue curve. But if we compute the Young modulus using the crosshead, we can obtain a totally different value. So we need to discard this value. So this is the importance of using the right instrument to measure mechanical properties of materials. So instruments are very important to characterize in the characterization of materials. Here I'm going to talk a little bit about characterization of anisotropic materials. So I'm going to present some preliminary results of a project I was working on, and it consisted of obtaining the material properties of 3D printed materials, printed at different orientations. As you can see in the figure, we consider orientations from 0 degrees to 90 degrees to see how the material properties change at each direction, to investigate what failure criteria for anisotropic materials we can use. So as I said, for this project, we use 3D printers. The material is PLA, which is basically a rigid plastic. So the specimen geometry was in accordance to the ASTM 638 standard. And once we have the specimens, what we need to do was to perform several tensile tests, as you can see in the figures. So in the figure on the left, you can see some marks that are called the length of narrow section, where the specimen is allowed to fail. And figure on the right, you can see the setup of the specimen and the appropriate tensometer for this type of material. As I mentioned, this is a rigid plastic, so we need to use this specific type of tensometer. This is a short video where you can see how this rigid plastic failed. And as you see, the failure is exactly at the middle for this type of orientation. Okay, these are some of the results that we can obtain. This is the stress versus strain curve. From this curve, we were particularly interested in the joint modulus of the material and in the yield stress. So we can obtain this data from this graph, but I'm gonna show you. Can you see this? Okay, this is the data that I obtained from the machine. As you can see, the machine, from the machine we can obtain the load and the displacement. This is the displacement that is obtained with the crosshead, and this is the displacement that is obtained with the tensometer. So this is the data that I obtained from the machine. So I can process that data, and from that data, I can obtain my stress versus strain curve. And from here, you can see that this material clearly has a linear part. So I can use this linear part to obtain the joint modulus, as you can see here in this figure. And to obtain the yield strain, I'm using the 0.02% strain criteria that consists of plotting a line parallel to the first portion of this curve with that 0.002 offset strain. So the point where the line and the stress versus the strain curve intercepts, this point corresponds to the yield strain. So in this way, we can process the data and we can obtain these two material properties for this type of material or for whatever material. This is just some summaries of the results that we obtained. This is the results for the 0 degrees, 45 degrees, and 90 degrees. And this is the average values for the tests that we perform. As you can notice here, as expected, the maximum strength was obtained for the specimen that was printed at 0 degrees. And there is we have some errors performing these tests because for some reason the specimen that was printed at 90 degrees is stronger than the ones that was printed at 75 degrees. So we need to do some corrections on these tests, but this is just to show you the data that we are obtaining from these tests. So this is a curve that relates the maximum strength with respect to the orientation, and here we are seeing the yield stress versus orientation. Here we're seeing the joint modulus versus orientation, and this figure here we have the average curve of each orientation, and you can clearly see that the strength reduces as the orientation changes. These are a picture of the failed specimens after the tests are done. Here is just something that we wanted to talk about just a little bit. With the universal testing machine, we can use different type of properties. For example, lattice structures are a type of engineering structure that are designed with a repeated pattern of interconnected unit cells. These structures are based or inspired on nature, and researchers have found that those structures have material properties that make them ideal for application in different engineering fields. Okay. Here we can see a 3D printed configuration of the unit cells based on the last slide that I showed you. And to characterize the behavior of these metamaterials, we can use the instruments that we have mentioned so far. So, for example, we can perform compression tests on these unit cells to measure the behavior of this type of materials. So these tests involve compressing a single unit cell of the lattice structure using a testing machine. So while measuring the load and the deformation response. So the goal of this compression test is to determine the compressive strength, the compressive modulus, and other mechanical properties of the unit cells that can be used to predict the behavior of the entire lattice structure.
So I'll be explaining about the strain gauge and how it works. So it is a device that measures the strain of an object. As we know that strain is the amount of deformation an object undergoes when subjected to an external force. So strain gauge can be used to measure the strain in varieties of materials, including metals, plastics, and composites. So how does a strain gauge works? So it works on the principle of the piezoresistive effect. This means that when the material is subjected to strain, its resistance changes. A strain gauge consists of a thin metal foil or a wire that is attached to a backing materials, as you can see from the figure. When the material is attached to a subject strain, the metal foil or wire stretches or compresses, and it causes its resistance to change. So that change in resistance can then be measured and used to calculate the amount of strain in the material. So what exactly is Poisson's ratio? So in simple terms, it's a measure of how much material will deform in one direction when it is stretched or compressed in another direction. So more specifically, the Poisson's ratio is the ratio of transverse strain, that is the change in width or thickness, to the axial strain, the change in length when the material is subjected to a tensile or compressive stress. So in this, as you can see, you can imagine having a play dough. So when you stretch it or pull it apart, it gets wider in the direction you pull it. And when you, at the same time, it also gets thinner in the direction perpendicular to it. So for another example that I can give you is, if you have a piece of rubber that's stretched in one direction, it'll also tend to contract in the perpendicular direction. So the ratio of this transverse contraction to the axial extension is known as Poisson's ratio. In this test, we got the results and we calculated the average Poisson's ratio for all three. And we got the average Poisson's ratio as 0.35. And it sits well with the knowledge that most materials have Poisson's ratio values ranging from 0 to 0.5. And that's about it. Thank you very much.
Thank you. Is there any question? Do you have any question? No? Okay. Thank you, Tenzin and Rodelio. And Camden and Jacob, are you ready?
Yeah.
Okay.
Yeah, we are.
Please start your presentation.
Can you guys see that?
I can see.
Okay. All right. So the topic we picked to do for this is nano indentation. It's by myself, Camden, and my partner, Jacob. So I'll let Jacob discuss a little bit about the principles of nano indentation.
So as a bit of an introduction, nano indentation is a nanomechanical test. It allows to provide a variety of different mechanical properties, all from a single test and or multiple tests. So in these tests, you can find the hardness, Young's modulus, the material stiffness, fracture toughness, delamination, and others like strain rate sensitivity and stress relaxation. Now, and unlike traditional indentation testing, nano indentation can be applied to small volumes of materials, things like thin films for electronics, carbon nanotubes, thermal coatings, some alloys, and composite materials like ceramics and concretes. It's also one of the fastest techniques currently because regular uniaxial, tensile, and shear testing, those methods usually take days from sample prep to obtaining the final results. So further on the principle, these nano indentations, you use a small diamond tip, which is be as small as 100 nanometers. That tip is then used to indent on the surface of your test sample. That indentation has an applied load and that displacement is measured. Now, the substrate or the material that is being tested can be moved laterally to perform tests that are perpendicular to the surface, such as shear test or scratch testing. And these indentation tests also have different tips that can be used to perform various mechanical tests. So you have quite a few. We can see some to the right here. The triangular prism tip right there is for Young's modulus and hardness. A spherical tip can be used for stress and strain. The flat punch, the cylindrical tip, which would be used for looking at the complex modulus of your sample. You have a cube corner for fracture toughness, a spherical cone, which would be used for scratch measurements, and you can use a wedge tip for 3-point bending test. So here we have the indentation depth when the tip has an applied load to the surface of the material. You can use that depth to calculate the contact area that the tip is left, and based on that area is dependent on the tip that you use. So the hardness and modulus of elasticity, or Young's modulus, can be determined using this contact area, the applied load, and the unloading stiffness. So if we look here to the right on this image, we can see there's a cone tip that is applied. It's left a maximum height from the surface to the max depth of the indentation. And there's also a contact height from the max depth to where the tip no longer has contact with the material. And that contact height is in a relation with the max height minus the strain times by the load force, and then divided by unloading stiffness. And the area, as I mentioned, the area you can find includes a contact height, and this F right here is a function dependent on the type of tip that you use. You find the hardness with tests like this. It's your loading pressure and divided by your area, and then things like Young's modulus right here is in relation with the square root of pi divided by 2 times by the unloading stiffness divided by the square root of the area. And here there's a sample graph of your load and displacement of this arbitrary indentation test, and the slope of that line is your unloading stiffness. So you can also do with these nano indentation tests, you can have dynamic temperature for these tests, which in the dynamic temperature, the sample is heated to a desired temperature before you do these tests, and also that the tip that is being used is also heated up to the same temperature. And these tests allow for to determine temperature effects on materials and composites. So if you look here to the right, you can see there's a diagram. The lower right image is a diagram of how you might heat up your sample and your tip. So you have a laser that is hitting a mirror at a 90 or at a 45-degree angle to reflect onto the sample to heat it up, with an optical fiber in the tip to heat it up to an equal temperature. So, which allows you to have these dynamic temperature measurements, and using it, you still have the same methods of finding the modulus hardness with these dynamic temperature tests. And the top graph here, on the top graph here, we have, it's an example of a heated up titanium sample, ranging from 20 degrees C to 500 degrees C. And we can see that the slope decreases as your temperature increases, showing that the unloading stiffness on these samples also are decreasing. So another test that is for these nano indentations is a scratch testing. These are accomplished by you apply a normal force to your material and you move your sample laterally, and that movement, that is the force that is required to do that movement on your sample, is what you measure for the scratch testing. It is useful for delamination, and delamination is the separation of the material parallel to the surface. And when you're doing these tests, your normal force on these can be either constant or dynamic, which can be helpful. It's relevant for different materials that need to have precise surface patterns for optical properties, such as like optic fibers, lenses, protective glass coatings, and such. So here on the top graph right here, or this top image, you can see there's a scratch test of a, I think on the paper it was referring to a protective coating. And so you can see the sample was moved across, and the red elevated portion is a buildup of material as the scratch test was performed. And here on the below, you have force measurements of scratch testing on a various sample.
So the next test that can be done with the nano indenter is very similar to scratch testing. It's the moment or shear testing. It's like scratch testing in the way that the indenter does move laterally, or the substrate moves laterally, but it does not penetrate the surface. Typically, this is done on samples where there's a nano protrusion that you would want to measure the mechanical properties of. So there's a force applied at the free end of the protrusion, quite like a cantilever beam, and the shear stress or the lateral stress is then measured. So this can be useful for things like testing the bond strength in selective layer depositions at the interface, or it can be used to test the relaxation modulus of different micropillars, like if they're created with PDMS. So yeah, the substrate moves laterally to the indenter tip. The force applied to the protrusion is measured until the interface either fails, or if you're testing for relaxation modulus, you would stop short of that failure. The last test we're going to talk about before getting into some examples is cyclic indentation. So this is a fatigue characterization technique where there's a repeated loading and unloading in the same spot over time. You can choose the frequency of indentation, the depth, and how many times you want to do it. So I think that's a pretty straightforward one. So getting into some relevant examples that we have, the first one's going to be measuring the fracture toughness of a brittle material. In this case, it's a fused silica shale subjected to nano indentation by a cube corner tip. So you can see the picture there in the top right. It was indented with some tip, the cube corner tip, and there was a radial fracture from each corner. So using optical imagery, you can measure the distance of each of those fracture patterns, and you could label these C. The penetration depth and applied load are measured as we usually do and used to calculate the hardness in Young's modulus. And then using all of these values that you've then collected, you could calculate the fracture toughness using the equation I have there on the bottom. The next relevant example would be used for carbon nanotube compression. So carbon nanotubes are very small objects at the nanoscale, so it's hard to use other testing techniques to get the material or mechanical properties from these. So in this test, they had vertically aligned carbon nanotube forests that are subjected to a compression testing with the nano indenter, and that the cylinder-like tip to determine the Young's modulus and stiffness. In this case, they had the stress-strain curve instead of load displacement, and then using the slope of the unloading curve, they were able to calculate the Young's modulus was 3.3 megapascals. So here's an example of how you would interpret results that you get from a nano indenter. So this was done on thermally oxidized silicon thin films. So you have your force displacement loading curve on the left, and using the slope at the initial point of the unloading curve labeled S, you could find your unloading stiffness. So this was 1200 micronewtons divided by 52 nanometers, which yields 22,854 newtons per meter for the unloading stiffness. The paper gave a contact height of 61 nanometers, and then using that contact height and the formula for the contact area for a Berkovich tip, which was used here, 24.56 times the contact height squared yields 9.1 times 10 to the negative 14 meters squared. So using all those values, you can calculate the hardness and Young's modulus for this silicon thin film. So moving on to some advantages of nano indentation, I think the most obvious one is it can be used on small volumes. So as things become smaller and smaller, we have to find new ways to test them that can't be done using conventional indentation or mechanical testing. So this would be useful for things like microelectrical, mechanical devices, medical devices, microchips, just things where there's no empirical understanding of how they interact at that scale. So the best way to do it is to do testing. The next advantage would be able to find local mechanical properties. So obviously we're indenting a small area, so the mechanical properties that are found are going to be local instead of global. So this can be used to determine properties in homogeneous and heterogeneous materials. So things like composites, you may have two materials very close to each other, but you can measure in both areas what the mechanical properties would be, and then also measure them together. So like I said, conventional methods can only obtain global mechanical properties. So if you want to find something that's local, you're going to have to use a test like this. And then finally, the limitations of nano indentation. So the first one is going to be something called pileup and sink. So as material deforms, the contact area can change with the tip, and this is going to affect the hardness results via strain hardening and pileup and softening and sink. The way in which this happens is not well understood, so it's hard to adjust your results for this. So the typical way that people do this is using AFM plots and image analysis. You can approximate the contact area that was present during the test. So if you look there in the top right figure, you get an example of pileup. So that's the material moving out of the way and pressing more against the tip, which will give you a higher contact area, and then sink. As it moves away when you indent, you get a lower contact area. Both would adjust how you calculate your hardness and Young's modulus and other mechanical properties. Another limitation is using it on soft materials. So soft materials are intrinsically challenging because they have adhesion, surface detection is difficult, and there's a high dependency on the tip. But there's also critical issues with measuring the hardness and viscoelasticity. So with hardness, you want your stiffness and sample to approximately match in hardness or in stiffness, or else the tip will go through the sample without measuring any data, and that's never good. You want your data. The second would be the viscoelastic properties of the material are obtained from nano indentation are very dependent on the oscillation frequency that you use and the tip shape, so you have to account for that. The third one would be tip dependence. So I've talked about tip dependence a couple of times now, but the interpretation of your results relies heavily on the tip shape and size. So things like your contact height, your contact area, all rely on that. Additionally, when you're doing different tests, matching the tip to the test is important. Each tip has a purpose, like was stated, I think, in the second slide. So using different tips for different tests may not be optimal. And this is shown in that bottom right figure. You have two different tips, the Berkovich and cube cone, used in the same indentation, and you get different results. So you want to keep that in mind when you're planning out your tests. The last one would be scale effects. So mechanical properties exhibit a dependence on depth. Materials have shown to be harder at shallower depths. So if you're nano indenting, you're only going maybe 100 nanometers into a surface. So you have to keep in mind that those results may not be the same that you would get from a shallower depth or a larger depth. So a good example of this is when you measure the hardness of gold at 5 nanometer indentation depth, you're going to get a hardness of 2 gigapascals. But at 100 nanometers, you get a hardness of 0.5 gigapascals. And then for large scale nano indentation, 0.1 gigapascals. So just keep that in mind. That's all we have. Do you guys have any questions for us?
Questions? Great presentation. Thank you.
Thank you.
Yeah. Next is Brian and Muncher. Brian, Muncher, are you ready?
Yes.
Okay, go ahead.
So our presentation is on fiber optic hydrophones and ultrasound transducers. The basic way to get the data for these instruments is through their signal conditioning of piezoelectric sensors. So the basic theory behind piezoelectricity is based on the electric dipole effect, which is that they are typically ionically bonded crystals, and at rest, the dipoles formed by positive and negative ions cancel each other out due to the symmetry of the crystals, which you can see over here on the right. The dipole moments form an electric field across the crystal, and this causes material to generate an electrical charge that is proportional to the pressure that is applied. The material needs to be conductive on either side so that the piezoelectric material can supply this voltage to the material itself. And in this case, the crystal structure that was used for getting this data was a PZT crystal structure. This is a ceramic perovskite material, which shows the piezoelectric effect, meaning that when this compound changes shape, the electric field is then applied. As I was saying before, this instrument is a hydrophone, which works by converting the sound waves into electrical voltage by detecting the changes in pressure. Now, there's some issues that may come with this, which would be different other noises that are received by the hydrophone. So there needs to be a way of kind of filtering that out. But the hydrophone picks up acoustic pressure, acoustic intensity, temperature changes, and the vibration mode shape, which is what was used in the example that you'll see later. This here on the right is a picture of a fiber optic hydrophone. There are other types of hydrophones that are like a membrane hydrophone, a ball hydrophone, and a needle hydrophone. But as I said, this is what was used in the data you'll see later. The sensing mechanisms for a fiber optic hydrophone is based upon the detection of acoustically induced changes in the intensity, phase, or polarization of light in the optical fiber. The first case is which the acoustic field modifies the properties of light guided within the fiber optic itself. The latter case uses the optical fiber they act as a conduit for delivering light to and from the sensing element at the tip of the fiber. For the general sensor models for a piezoelectric system, you can see that in this first figure, the change produced depends on a piezoelectric constant of the device, and is determined by the area, the width, and the dielectric constant of the material.
So this is just a basic idea of what the system should look like. But for ours, we needed to use a KLM equivalent circuit. In this model, you can see that there's this conversion up here because it is not traditionally used for piezoelectric systems. So just kind of change some of these symbols for what is shown up here. The V3 and I3 are the respective voltage and current applied to the piezoelectric crystal, which produces the resulting acoustic force and the particle velocities. You can also see that here are the two particle velocities inside the crystal. The model also includes the thickness of the crystals here, which create different values based on the values given. The equations on the right here are then used to convert the electrical signals into the physical properties that are needed for the hydrophone. Here's just kind of a condensed version of the piezoelectric transducers. The thickness of the expander plate, the end of electrode expander bar, are these values I was talking about earlier that when given a variance can change the output of the system. There's also axial symmetric mode and thin rings that the spherical systematic mode can be used, and we can use this to find the resonant frequency of the material. Did you want to start sharing yours, Manshul?
Okay. So I'm going to explain how to measure the acoustic pressure using the hydrophone. So I just give you some examples with the hydrophone. If you can see this is the transducer and this is the tip of the hydrophone. If the acoustic wave is hit the pressure, it the voltage the sensor shows the voltage output. So every sensor has the own sensitivity. So the sensitivity unit is voltage over megapascal. So it is easy to convert to the acoustic pressure from the receiving voltage. So every frequency has the sensitivity is different. So we can find the acoustic pressure at specific frequencies. So and another data we can get the acoustic intensity. You can see the unit. This is the power per unit area. The acoustic intensity is also easy to get because the equation is acoustic pressure square over density of medium and speed of sound. So the acoustic intensity is proportional to the pressure square. So can get the power of the
acoustic sound. So this is the example of transducer. So the PGT is one of the piezoelectric transducers. So the resonance frequency is 2.3 megahertz, and the frequency sweep profile is, you can see the left side, and if the converter to the pressure, from pressure to acoustic intensity, you can see this profile. So you can get the acoustic intensity. So this is, I will show you two kinds of special shape of transducer that I fabricate before. And I will show you the simple example of the what kind of measurement I did using the hydrophone. So basically, this shape is we called omnidirectional transducer. It made of barium titanate, which is piezoelectric material, and I call this is BTO transducer. So usually the rectangular shape transducer is used, but there is a direction. Usually there is a direction, so I want to verify the spare can transmit it and receiving the same power regardless of the direction. So I compared the resonance frequencies and with respect to the angle, but I will just show you the simple example. So this is the experimental setup of the transducer I made as a receiver, and this is the real photo of the setup. So this is this transmitter make the acoustic wave, and the receiver will get the electrical signal, the voltage from the acoustic wave, and hydrophone sensor also get the same thing. So you can see the signal from input signal is the yellow. I will and the receiving signal is green color, and the blue signal is fiber optic hydrophone. Then we can convert how much the acoustic power is received. So this is also the setup, but this BTO transducer as a transmitter. So if the input is go to the this transducer, the hydrophone get the receive the how much power can receive from how much acoustic pressure can receive from the transducer. So the green is the input signal, and the not the blue, yellow is the received signal. You can see the time difference. This is distance. So when the transmit the acoustic wave to the hydrophone, I did the frequency sweep from the 500 to 500K to 3 megahertz. So when the 675 kilohertz at the at 675 kilohertz, the acoustic pressure was the highest value. It means the the resonance frequency is 675 kilohertz of this transducer. So to compare the measurement and the calculation, I found some equations. There is so many parameters, but this is the equation of the frequency, resonance frequency. So we can just find the elastic compliance. So there is a S11 and there is a S12. So I found the elastic compliance. So the frequency resonance source for calculation is 815 kilohertz. It's different, slightly off compared to 605 kilohertz, but because of the fabrication error. And also the another example of the I fabricate the transducer with PVDF. PVDF also the one of piezoelectric material. So this is also special shape of the transducers. So if there is many eigenfrequencies, if they are complicated shapes, so it means we can get some broad we can have application of the broad range of frequencies. So so this is the simulation of vibration mode shape. So from this transducer, there is a vibration mode shape. So it moves like left to the right, front to the back, like here. So the mode shape is different and at the different frequencies. So this is all eigenfrequencies. So actually, this is not the range of the ultrasound, but I try to compare. I try to measure the vibration shape to compare simulation and real experiment. So I put some multiple points and to compare the vibrator mode shape. The frequency shift range is 200 to 5K hertz. So this is the real photo of the my transducer and the fiber optic sensor. And each point I put the fiber optic sensor is close to the transducer. So I can detect the local point of vibration. So this is the compare the simulation and experimental data. So at the 7 kilohertz, I found the similar mode shape, and at the 800 hertz, I found this kind of similar mode shape. At the like this is also similar, and this is also similar. This is also similar mode shape. This is also similar mode shape. So basically the frequency is slightly off, but this is the difference between the measurement and experimental. So So I show you the measurement data and analysis the finding resonance frequency and vibration mode shape using the hydrophone. And this is that's all for the presentation.
Okay, thank you. Do you have any question? Okay, thank you, Victoria and Brian. And Tauran and Diana, are you ready to present your instrument?
Yeah.
Okay, let's start.
Hello. Can you see the presentation?
I can hear, go ahead. I'm
Okay.
very steady.
Hello, me and Taran would like to talk about an existing field of computational technique called molecular dynamic simulation. We will go over molecular simulation to molecular dynamic simulation, performance application limitations of molecular dynamics. So introduction to molecular simulations. Molecular simulations are a common technique used in scientific world, and they're using computer experiments in which one controls the system details and basic time evaluation. And the goal of such a simulation may vary, but typically we're interested in our equilibrium properties. And depending on what you're testing or trying to simulate, we need to use various skills, and it will depend what kind of approach we're going to be using. We're going over molecular dynamics, and it assumes atoms and molecules. So it will be an atomic scale, but in general, you can also simulate from a quantum scale to a macro scale. Molecular dynamics simulation are computer simulations that use the laws of physics to study the behavior of molecules over time. They allow us to simulate the movement of molecules in different environments, such as gases, liquids, and solids. And that can provide us insights into the physical and chemical properties of materials, including stability, strength, or flexibility. That's really important for engineering world. And our physics involves the energy function and Newton's laws. Oh, there is a simple algorithm on the left of the slide. To perform a molecular dynamic simulation, you need to have three key components. Firstly, we need a molecular system or a model which can be built using software such as PIML or VMD. This model should represent a system of interest in as much detail as possible, including information on the atomic structure and the interaction energies between atoms. And then we need to divide time in discrete time steps, no more than a few femtoseconds, and extend to the negative 15 cents each for our scale. And the next step is to choose a suitable force field. The software is responsible for solving the equations of motions and calculating the position. And the force fields, on the other hand, provide a mathematical function to calculate the force acting on each atom or molecule. There are many types of force fields available for molecular dynamic simulations, each with its own strengths and weaknesses. Some of the most commonly used force fields include the UFF, CFF, MF94, MM234S, Charm, Amber, Crumbs, Ovals. And each force field has its own set of parameters which need to be carefully chosen to ensure that the simulation accurately represents the physical system. So in addition to the force field, there are several factors that need to be taken into account while performing molecular dynamic simulation. So first, we're choosing our force field preparing our molecule. And then we need to include the size of the simulation box, the choice of the simulation parameters such as time step, integration method, and the selection of the appropriate boundaries. Then we can run our simulation, get our results, and analyze our data. And I will pass the next slide to Taran. Thank you.
Thank you, Diana. Okay, let me share my screen. Can you see my screen right now?
I can see. Go ahead.
Okay. Okay, thanks, Diana, for introducing the principle of MD simulation. Now, I will demonstrate a study of the mechanical property of cement by MD simulation. So as we all know, the concrete is the largest material by volume that is used in construction. Its use expected to double in the next 30 years. So following the bottom-up research philosophy, the cement paste as the most important component of concrete account for the mechanical properties of concrete. So in ordinary Portland cement powder, there are 4 major manners as shown in the table on the right side. That is tricalcium silicate, dicalcium silicate, and tricalcium aluminate, and terracolimate aluminate ferrite. So when a hydration reaction occurs in the production of cement, the main hydration product named calcium silicate hydride, also as a CSH, is generated and bonding the other component together as a function of the glue. So that is the key part of the cement. Thanks to the revolution of experiment technology, researchers found that the nanostructure of CSH is similar to a natural mineral named tubermarite family. Due to the differences in interlayer space, it has 3 substructures named 9 angstrom, 11 angstrom, and 14 angstrom as shown below. And these 3 structures are used in the following MD simulation. So first, we calculate the mechanical properties of each structures. In a canonical ensemble, the average shape of a periodic structure can be described by 3 cell vectors, A sub 0, B sub 0, and C sub 0. So typically it's represented as columns in the matrix H0 sub 0, yeah. And the determinant of H sub 0 corresponds to the volume. And when the structure is deformed, the cell vectors change to be A, B, and C, and the cell matrix becomes H. So the 2 matrices, H sub 0 and H together, define the strain tensor epsilon. At the equilibrium state, the H equal to the H sub 0, and consequently the strain vanishes. That is epsilon equal to 0. So by definition, the strain tensor is symmetric. And the strain tensor epsilon is associated with the stress tensor sigma. Together, they define the change in free energy of deformation. The stress tensor is obtained as the change in the free energy A with respect to the strain at a constant number of atoms and temperature. For orthorhombic material, the elastic constant and flexibility constant should be simplified into 9 independent variables as shown below. So after simulation, the volume modulus, shear modulus, Young's modulus, and boson ratios were calculated using Vergeet-Russell-Hill method. Also, it can be seen that the results obtained in this study are similar to the other references. Since the CSH is an amorphous scale, we assume it's a composite material with 3 different amounts of the tubermarite family. and the Young's modulus and the boson ratio in two porosities is calculated based on three methyl mechanics method. As you can see, the Young's modulus result as obtained by using the Vogt and the MT method are closer to the experimental result. However, the boson's ratio result as obtained with the SC method are closer to the experimental values for low porosities, and the result obtained by using the MT method are closer to the experimental ones for higher porosities. So those discrepancies demonstrate that the current method is not suitable for amorphous materials, and the mechanical properties of CSH could not directly derive from those equations. So next thing, we would like to dig in depth to investigate the structural behavior of the CSH under tensile loading. So we built 3 supercells of the CSH with different calcium silicate ratio to representing the beginning state, mid state, and later state of the hydration reaction respectively. So here on the left side is the trajectory of one structure under tensile simulation. As you can see, it shows that the structure falls due to the shear stress and follows 45 degrees of the cross section. Also, in the stress strain curve, it demonstrates a different fracture behavior. So by performing the concentration analysis and the MSD analysis, we found that the binding interaction differences are basically caused by the situation that the electrostatic and bonded interactions between adjacent layer and the interlayer calcium are replaced by the water molecules. Also, the water molecules distributed in the region of the interlayer have an impact on structural deformation in Z direction during the process of the tension. The water molecules located in the interlayer region have dynamic and structural properties due to the electric influence and structural constraint in the calcium silicate layer. Water molecules between the calcium silicate layer show the dipole orientation, good organization, and high density. Finally, the pros and cons of MD. The advantage of MD is that it could be applied in various fields such as biochemistry, drug design, and material science. And it could also interpret the experiment phenomenon and help us to improve the design of the experiment. Also, it's a simulation method that closest to the experimental conditions. But the disadvantage of MD is that it's a limitation of the simulation time, and the accuracy of the simulation result is highly dependent on the parameters of the force field. Also, it ignores the contribution of electrons to the system energy. That's all. Thank you. Any questions?
Thank you. Do you have a question? No? Oh, yeah. Very nice to talk. Thank you for presenting your instrument. Yeah, we are going to stop here and let's meet next to Tuesday. Thank you.
Thank you.
And yeah, and then send your evaluation sheet to me by tomorrow, and I'll do my best to upload the grading this weekend. But I will let you, yeah, I'll do my best. Yeah, thank you.
Sorry, I have a question. What we fill for the evaluation? Do we need to fill the summary and comment? Okay.
So summary of comments. You please fill out the summary and comments of the other group's presentation, because sometimes students didn't listen to others group's presentation. So I would like to avoid this situation. So I ask you please fill out the comments and summary of other presentations.
Okay.
Okay, thank you.
Thank you.